Well, thank you all very much for coming. My name is Ian Clarke. I'm the founder and architect of Freenet. Just a quick overview. As I just said, I'm the founder and architect of Freenet. Freenet is a 25-year-old nonprofit organization dedicated to creating technology that keeps the internet free, in essence. I'd like to thank FUTO for both hosting lunch and also funding our work. Last September, I think it was, I gave a talk at this same lunch where I focus more on how to build things on Freenet. If you're interested in seeing that talk, not right now, but you can find it on freenet.org. This talk, I'm going to focus more on the inner workings of Freenet, the kind of problems that we encounter building a truly decentralized internet. But if you haven't seen the previous talk, don't worry, because I will start by giving a little bit of background about what Freenet is. And there'll be a Q&A at the end, so please think of questions and you can ask them then. So what is Freenet? Well, I'll start with a simple view of what the internet looks like today. You have the user, and the user interacts directly with software on their computer, typically a web browser or maybe an IM client or perhaps a game. That software then uses the internet protocol and UDP and TCP on top of it to communicate over the internet to predominantly web servers, which are backed by databases or publish-subscribe systems. All of these technologies that sit within data centers, typically controlled by one of about 5 large corporations. The vision with Freenet is different. So everything the user interacts with is the same, but instead of connecting over the internet to a series of data centers, with Freenet, we run a small piece of software called the Freenet core, which is about 5 or 6 megabytes, which is really nothing by the standards of modern software, which runs on the user's computer. And it's peer-to-peer software, so all of the other people using Freenet are running the same software, and collectively, all of these Freenet cores form this global decentralized network that's designed to replace the centralized technologies that we currently use, whether it's search engines or instant messaging systems or any of these other technologies. So how does it do this? Well, Freenet is fundamentally a distributed key value store. In software engineering, you encounter key value stores all the time. They're variously known as hash maps, hash tables, dictionaries, or associative arrays is an older term I hadn't heard in a while, or keyed collections is the more general term. With Freenet, and the way all of these things work is that you have a key, and using the key, you can retrieve the corresponding data from the data structure. With Freenet, the key is a Blake3 hash of some WebAssembly code. This is probably the most unique property of Freenet, where this WebAssembly code wraps a value or some state, which is just arbitrary data, could be text, could be images, could be a movie, really anything you like. And the role of that WebAssembly code is firstly to decide, is that data permitted under this key? A very simple example of how it might do that is it might verify that the data is accompanied by a specific digital signature. But it can be a lot more sophisticated than that. The second thing the contract is responsible for is controlling how that data can be modified. when you want to modify some data in Freenet, you send what's called the delta, which is essentially a description of a modification to the data, and then the contract will decide, is this change valid or not? So that might also be based on verifying that it's accompanied by a digital signature, but it can get a lot more sophisticated than that. And then the third thing that contracts are responsible for is telling Freenet how to efficiently synchronize that data across the internet. So that might be, for example, using kind of hot topic right now, conflict-free replicated data types. But the point is that you can implement whatever synchronization algorithm makes the most sense for your data. And then the other thing these contracts can do is they can read the state of other contracts in the network. So this opens up a lot of possibilities, as you can imagine. So what does this look like from the perspective of the user? So, for example, if you're using a web browser, the Freenet core exposes a local web proxy. So you can type HTTP localhost : whatever the port you're running on is, / and a key, and that will the Freenet core will then retrieve the data that corresponds to that key from the network, and it will supply it back to the web browser, and that will actually be just literally a zip of HTML files, JavaScript, or potentially WebAssembly, anything that can be understood by the web browser, and the web browser will then interpret that as a web app, and it'll start up a user interface in the web browser, which can then connect back to the Freenet core over WebSockets and read, write, modify contracts, do whatever it wants, but it's all mediated by the web browser, and so this user interface can really do whatever a web browser can do. I will point out, though, you don't have to use it through a web browser. You could also build a native app or a game that can communicate with the Freenet core over the same API that the web browser is using. So it's extremely flexible. But the benefit of the web browser is that you can actually download the user interface itself over Freenet. So when you go to the web browser and give it this key, how is it actually finding the data? Freenet is a distributed decentralized network, so this data is distributed across potentially millions or tens of millions of peers in the network. And there's no centralization, so there's no kind of central directory or database that keeps track of where the data is. So how do you find it? Well, every key can be mapped to what we call a location, which is a numeric value between 0 and 1. So in this case, this key is maps to a value of 0.75. This little gray circle here represents your local Freenet core. Every peer in Freenet also has a location in the same space. So in this case, it's 0.32, which is not really close to what we're looking for. So what that peer will do, every peer is connected to maybe 20 or 30 other peers in the network, and each of those peers also has a location. So in the simplest case, the peer will simply say which of my neighbors is closest to the data that I'm looking for, and it'll route the request there. And that process will be repeated until it rapidly homes in on the data and retrieves it. This algorithm this small world algorithm is very scalable. It's got logarithmic scalability characteristics. So it scales the same way as a hash table or a hash tree or any of these data structures. So it can pretty much scale indefinitely. But when a peer is trying to find a specific bit of data and it's deciding which peer to route through, there are a variety of approaches. The simplest approach, which I just described, is called greedy routing, where you just route the request to the peer that is closest to the data that you're looking for. And that works, and that's how the very first version of Freenet 24 years ago actually worked. But we can be smarter than that. If really the ideal routing algorithm would figure out which peer is going to respond fastest for a specific request and route there. So how do we do that? Well, taking a step back, one of my favorite algorithms is called isotonic regression. And isotonic regression is where you have two variables. In our case, let's say it's distance. So it's the distance between the key that you're looking for and the peer that you're thinking about routing to, and response time. And one of the characteristics is that we would expect, on average, that the closer you are, or the closer a peer is to the data you're looking for, the faster it will respond to that data. And that's what's called an isotonic relationship. When one increases, the other increases. When one decreases, the other decreases. Another example of an isotonic relationship is the force you're applying to the accelerator in your car and the amount of acceleration you're getting. So one increases, the other increases, and vice versa, but it's not necessarily a linear relationship. It might be some kind of curve. You don't know the exact relationship, you just know it's isotonic. And in that kind of situation, that's where an isotonic regression is very useful. So what you can do is you can collect noisy data about, I tried routing this key and it took this long based on this distance. And there's going to be a lot of noise because there are a lot of other factors involved. But on average, you expect that relationship to hold. And in that situation, you can use an isotonic regression to extract a smooth curve that will fit that relationship. And one of my favorite things about isotonic regression is that it's non-parametric. So a different way you might solve this problem is maybe using a running average. But in the case for a running average, you need to choose what window size to use. So you have to choose a parameter. And most algorithms like this, you've got to choose parameters to tweak in order to get it working well. It's like the learning rate if you're training a neural network. But the beauty of isotonic regression is that as long as you know it's an isotonic relationship, that's all the algorithm needs to know. It will figure out what the curve is very efficiently based on the data available. And if you're interested in a Rust implementation of isotonic regression, specifically called pair adjacent violators, I wrote one. And you can find it here. If you code in Kotlin or Java, I also wrote a similar library for that language. In fact, that was kind of the prototype though. So the Rust one is better. So how do we use this? Well, I already kind of hinted at this, that let's say in the case of latency, we want to, how long is it going to take to retrieve the data given a particular distance between the key we're looking for and the peer that we're routing to? So latency in this case. We can use isotonic regression so the peer can experimentally collect data about this and learn what that relationship is. But we don't always find the data that we're looking for. So it's also possible that it will fail to find the data. We would also expect that if you're routing a request to a particular peer, the further away that peer is, the higher the likelihood that it will fail to find the data. And then also, after we found the data and the peer starts to send the data back, we're not sure how quickly that transfer will occur. We would assume that the closer the peer is, based on location to the data you're looking for, the fewer hops it will need to go through in order to retrieve the data. So we would expect, all else being equal, that transfer speed will be higher for distances that are shorter. So what a Freenet peer does is it collects data about the performance of other peers in retrieving data. It does these regressions, and then when it wants to route a request for a particular key, it will use this data to predict how long it's going to take, the probability of failure, and the transfer speed. And then for each individual peer, it will calculate an adjustment based on that individual peer's performance. And we're then able to combine those adjustments to come up with a score, which is essentially how good is this peer expected to be at retrieving this data, and we route the request to the peer with the best score. So when a peer connects to the network or wants to connect to the network, we have a particular process for that. So the peer comes up. Initially, it sends a connection request. So when a peer first starts, it needs to connect through a gateway, which is just another Freenet peer, which is not behind a firewall. Or if it is behind a firewall, it has port forwarding set up so that it can receive incoming connections that it's not expecting to receive. So the connect request will be, every connect request starts with a target location, which is essentially saying, I would kind of like to connect to a peer with a location close to this one. And in a moment, I'll explain how it chooses that target location. But the connect request is routed through the network in much the same way that a data retrieval request is routed. It's routed towards the peer that's closest to the target location at each hop, and it will route through several peers. And then some of those peers will decide, yes, I would like to be friends with this new peer. And so they each establish a connection back to the original peer that's joining the network. Some of these peers, in fact, most of these peers will probably be behind firewalls, and which is essentially like it's a computer behind a firewall is a little bit like a telephone that can make outbound calls but can't receive inbound calls. Fortunately, so this is obviously going to be a problem if you've got multiple peers, each of which are behind their own firewalls. How do you connect them? But luckily, there is a trick where if both peers are trying to connect to the other peer at the same time, it will effectively fool their firewalls into allowing them to establish a direct connection. This is called firewall hole punching or stun, or it's got a couple of different names. So that's what's actually going on here when these direct connections are being established. But the question is, how do peers decide which other peers they want to be connected to? And it turns out that a small world network, so the reason this routing works is because Freenet peers form a small world network. And what that essentially means is that peers that are close together are quite densely connected. They're a peer that's close to you, you're quite likely to be connected to. And a peer that's very distant, you're much less likely to be connected to. So this is the same as human relationships. You're a lot more likely to have a relationship with your next door neighbor than you are with a random person on the other side of the planet. And in fact, small world networks were first, I guess, discovered because they discovered that humans were very good at routing messages along through individual friendships in a way that's completely decentralized. So that's the origin of it. But we understand the mathematics of this pretty well, and we understand that the optimal small world network is when the probability of a connection existing between two peers is proportional to 1 over the distance between them. So when so a peer has a location and it's receiving requests from other peers. Because peers are routing requests to the peer that is closest to those requests, if you draw a graph of the requests that are being received by a peer, they will tend to cluster around that peer's location. And what we want in terms of a peer's connectivity is we want the distribution of connected peers that that peer has to roughly match the distribution of inbound requests that that peer is receiving. So you could kind of think of it in terms of, as a person, if people are constantly asking you questions about 1970s movies, then even if you don't know much about them to begin with, eventually you're probably going to become quite an expert on 1970s movies just because that's what everyone is asking you about. And that's great. You build up a reputation for knowing about these movies, and so more people ask you about them, and that ends up being a self-reinforcing emergent effect. So when a peer is deciding, like, what other peers do I want to be connected to, what it's trying to achieve is it's trying to have a distribution of connections that matches the inbound requests that it's receiving. So what it wants to do is it wants to identify parts of the key space, these numbers from 0 to 1, which are actually arranged in a ring. So 0 and 1 are actually, the distance between 0 and 1 is 0. But what you want to do is you want to identify parts of the key space where you're receiving a disproportionate number of inbound requests relative to the number of peers that you're connected to that are close to those requests. And so in order to address this, the peer will do two things. Firstly, if it notices that a certain part of its key space, if it's getting a lot of requests and it doesn't know very many peers, it doesn't have many neighbors in that space, it will initiate a connect request that is targeting that part of the key space. And then secondly, peers are constantly receiving connection requests from other peers, and they will decide whether or not to accept that connection request based upon whether the connecting peer is in a part of the key space that is underserved. So in terms of, so another problem that Freenet needs to deal with is resource management. So there are different types of resource that a Freenet peer needs to worry about. Probably the most important one is bandwidth. That's kind of the most scarce resource, specifically upstream bandwidth, but downstream also matters as well. Other types of resource would include memory, storage, CPU, all of the different things that are a finite resource that are consumed by a Freenet peer. And there are really two things that consume resources. The first is contracts, which we were talking about, because a contract is receiving requests, it's sending responses, it's also modifying the data associated with the contract. And then connected peers also consume resources because peers are constantly asking each other to retrieve information for them. So the question then is, we have contracts and connected peers are each consuming bandwidth, consuming other finite resources, but they also have a value. So the value of a contract where you're getting a lot of requests for that contract, that's valuable to be able to provide that information to other peers. So the value of a contract is proportional to the number of inbound requests that you receive for that contract. And then peer's value is kind of the opposite. The value of a peer is proportional to the number of requests that you're able to send to that peer. Now you might say, well, if what if you send a request to a peer and it's not able to respond, or it responds very slowly? Well, that's not really very valuable to you. But because of the other mechanism where a node is always trying to route requests to the peer that is most likely to respond quickly, if a peer is responding slowly, or if it's not able to find the data at all, then your peer will simply stop routing requests to it. And so you can actually just kind of say, well, the value of a peer is proportional to the number of requests we're sending to it, because if that peer is not doing a good job, then we won't send requests to it. And so the way that we do resource management is we're doing this cost-benefit analysis of both other neighboring peers and contracts. And if we hit a limit, so with Freenet, you specify what is the maximum amount of upstream bandwidth you want to contribute to the network, which will typically just be a tiny fraction of your available bandwidth, because we don't want the Freenet peer to interfere with your use of your own computer. But if the Freenet peer hits that, a question?
What's the difference between a contract and a peer?
The question was, what's the difference between a contract and a peer? So a contract is just the data that is stored on the computer, whereas a neighboring peer is a active connection to another peer in the network. So. No. So contracts and peers are not really the same category of thing. So so it's a connection to another peer in the network. Contracts and peers both have locations, but the similarity ends there. A contract is something that can be retrieved, whereas another peer is something where you can ask it to do stuff for you. Okay. So the peer is constantly doing a cost-benefit analysis to determine which contracts and which other peers are providing the most value relative to their cost in terms of the resource that's being used. And if the peer hits one of its resource usage limits, then it will simply start to either disconnect from the neighboring peers that are kind of more of a drain than a benefit, or similarly, they'll delete contracts, the least useful contracts relative to their cost. Now you might say, well, what happens when data falls out of the network? But because peers will effectively cache contracts based on how useful they are, if a contract suddenly becomes extremely popular, then it will automatically get much more widely cached within the network. If the contract maybe becomes less popular over time, then the network will automatically scale back how broadly cached that contract is. And so typically the only way a contract's going to completely fall out of the network is if there isn't enough demand for that contract to even justify it being stored by the peer that is closest to that contract's location. So just to talk a little bit about some of the things that we'll be doing in future. So right now, when some data is requested from the network, it the request passes along a request chain, similarly to a connect request. And then when it finds the data is sent back along the same chain as a response. And the reason it's sent back along a chain rather than being sent directly is because we don't want the requesting peer to have to establish a connection through the firewall to the peer at the end. So it kind of uses this request chain to send the data back through this chain of peers. But at the moment, the data must be sent in its entirety from one peer to the next before that peer will start to retransmit it to the next one. Now, this has the disadvantage that it means that for larger data, it's going to be slower to retrieve. But it has the advantage that it means that Freenet people are less likely to view Freenet like BitTorrent, which is kind of so it means that like worrying about kind of copyrighted material and that type of thing is less likely because Freenet is not at the moment optimized for the distribution of large data. But in the future, we will implement data streaming, so it will get a lot better than that. If you're just talking about relatively small data, like a megabyte or something like that, then this latency isn't really going to be much of a factor. And I think with that, does anyone have any questions?
Yeah, I just wanted to make sure I understood the relationship between peers and contracts. So if the idea is I create a contract and it's 0.03, then nodes that are peers that have a location close to that value, they're going to be the ones that are responsible for storing it. Is that correct?
Yes, that's correct. So in general, peers will prefer storing contracts that are close to them, partially because those are the contracts that they're going to receive requests for. So it's kind of a self-fulfilling prophecy.
Would a peer, or like, even if my location was far away, would I still cache like my own request and make that available, or?
Yeah. So peers will cache requests for contracts. So let's say if there was a contract that was extremely popular, where everyone wanted it, then that contract is probably going to end up getting cached by every peer. But as the demand for the contract decreases, it'll just tend to be cached on the peers that are closest to it.
Got it. Okay, cool.
Hi, I have a question about the score and how you keep score. So if I understand this right, each peer is keeping track of a score per contract per another peer. Is that right? Per.
It's the score is calculated as part of the routing algorithm. So the score is kind of calculated in the moment when the peer is deciding where to route the request.
For that contract.
For that contract.
Got
yes,
it.
exactly.
Okay. Cool. Thank you.
How does Freenet compare to alternative animals like Noster? Blue Sky has a protocol. There's things built on the ActivityPub. How do they compare and contrast?
Yeah, it's very difficult to do a kind of head-to-head comparison because each of those things is kind of quite different and quite complicated. But generally speaking, the unique thing that Freenet does is this idea where the data is identified by a hash of the code that specifies essentially the characteristics of the data.
Right, you hash the WASM contract, right?
Exactly.
The WASM module.
Yes, so that's unique, and that's really the heart of how Freenet tries to be a general purpose platform for distributed computation. I think the other general difference between Freenet and a lot of these others is that Freenet is a kind of end-to-end solution. So with Freenet, people can create decentralized software. Freenet helps people you discover the software that you want to use through Freenet, and the software is distributed through Freenet. In much the same way that with the World Wide Web, you install a web browser, you don't need to install anything else. You can go to Gmail, it'll download a web app that you're then using in your browser. So it's a little, the analogy I use is that a lot of these other options, it's kind of like a crankshaft. It's useful, but you need a lot of other components to actually make it do something useful. Freenet's the car. Like Freenet really does everything end to end. It lets you discover the software, it lets you get the software. You really just do everything through Freenet. It's a complete platform.
Is there any capability or function in these other alternatives that you would most be interested in adopting or hybridizing?
It's kind of tricky. Like a lot of the way Freenet's designed, it's like it kind of fits together in quite a specific way, and so it's not kind of Lego-ish. Like Freenet is really, more or less this version of Freenet is really the amalgam of more or less every good idea I've had over the past 25 years, or not just that I've had, but that I've encountered. I mean, some aspects of the current Freenet design are quite different to the original, and incorporates ideas that other people had. So Freenet is kind of it's the best aggregation of the best ideas that I've come up with. But that's not to say that I've got a kind of not invented. I'll plagiarize from anywhere if it'll lead to a better product at the end of the day.
Cool.
So clearly Freenet has a lot of utility, and I'm curious, 25 years ago when you began development, did you have a specific service or goal in mind that you built Freenet to pursue, or did you just sit there and think, I want to build a useful tool for people, this is the tool I have an idea for?
Yeah, it's so much history. It's almost hard to get it straight in my own head. But the original Freenet, really where that came from was I was studying computer science and artificial intelligence before it was cool, back in the mid-90s. And back then people would say things like the internet roots around censorship and all of this stuff. And as I started to learn about how it all actually worked, I realized that was BS. Like, actually, the internet was potentially the most easily censored and controlled communication medium anyone had created. And so the original Freenet, I kind of thought of it was almost like I was trying to build the thing that I naively thought was how the internet worked before I discovered how the internet really worked. And so it was very much kind of coming from, it was kind of a platform way of thinking about it versus having a specific application in mind. It was more like, I really don't like this tool that everyone's using. I want to build a better tool. I think that the problem with the original Freenet was there was some things I got right, like the small world stuff and all of that. And the original Freenet was the first distributed decentralized peer-to-peer network. And a lot of the ideas we came up with found their way into other cryptographic contracts, for example. We were the first kind of deployed version of that. But there was also a lot we didn't know. Like there are ideas in the new Freenet that are inspired by things like MapReduce, for example, which is a technology for distributed computation developed by Google, I think in 07-ish. And then, of course, a new Freenet relies on WebAssembly, which didn't exist 25 years ago. There was Java bytecode, but really not well suited to solving this problem. And so it's kind of a combination of things where there were some ideas that I just hadn't had yet at this point. And so the original Freenet, everything on the original Freenet is like a static website. It's just files, and you could describe it like a decentralized hard disk, essentially. The new Freenet I wanted to build a decentralized computer, like something that could actually do computation. And so that's, so it's a variety of things. It's ideas I hadn't had yet. I didn't know, back when I designed the original Freenet, there was no such thing as social media. I mean, there was Slashdot. That was about it. And, maybe IRC. So there was a lot back then where it just wasn't apparent how people would evolve to use the internet. Now, of course, we know that social media is critical, instant messaging is critical. And so the new Freenet is really designed to be able to allow people to build for these use cases that have now become the dominant internet use cases, but nobody knew what those use cases were going to be 25 years ago.
My impression from your slides was that the coordinate for peers and contracts for like the heuristic for where they're like physically located is represented as a one-dimensional number. What I was wondering was, when in the real physical world a client could be north, south, east, or west of another, how well does that coordinate map onto the real world, and does that cause any problems if it doesn't map well?
That's a great question. So small world routing, you just need some concept of location. The obvious concept of location is kind of latitude and longitude, which we're all familiar with. But with Freenet, we don't want it to map to real location directly. Firstly, because a one-dimensional location is just simpler to deal with. But secondly, what we don't want is for example, let's say if there was a controversial website on Freenet, if Freenet locations map to real world locations, then there will be some piece of geography where that controversial website is concentrated, and that would make it a lot easier for an adversary to attack. And so we quite deliberate. So locations in Freenet, the location of a peer is actually a hash of that peer's class C IP address. And so it's deliberately randomized relative to real world locations. However, because Freenet peers, when they make routing decisions, do consider things like latency, the network topology will tend to adapt to some degree to the actual real world latency, simply by virtue of the fact that that's what will allow it to retrieve data more quickly. But we quite deliberately didn't want Freenet's concept of location to map directly to the kind of real world geographic location, because it would make it too easy to attack.
So hypothetically, if there was like a physical region of the Earth in which many peers with a similar coordinate were located, and there was another faraway region of the Earth that had the same or a very similar range of coordinates, would the fact that those two are far away from each other, but similar coordinate-wise, like cause any issues, or would that just sort of be like automatically adapted for by the heuristics of like looking for latency and stuff?
Yeah, it could be like that. One of the real reason that we went to so much trouble to make it adapt to actual latency is to address that exact issue. Like if we just ignored latency, then you could have a ridiculous situation where a single request might go like US, Australia, Europe, New Zealand, and it would just, because the concept of location has no relationship to real world location, it could be extremely inefficient. So the assumption is that because it's adapting to actual latency performance, there will be some mapping between real world location and network topology, but not so obviously that it would make it easy to kind of pinpoint and attack particular contracts on the network.
Thank you.
I'm sort of, I guess this is sort of orthogonal to the design of Freenet, but I'm wondering, do you have a sort of like particular way of testing your implementations of distributed systems? Like I know there's sort of like the random testing, and then there's like all the way on the other end of the spectrum, there's like formal verification. And I'm wondering if there's anything in particular that you like to do to try to sort of like have a better guarantee that it sort of works.
That's a great question. I'm glad you asked that. So yes, so it's kind of a layered approach. One of the things that makes building something like Freenet particularly difficult is that an individual peer can behave exactly as you think it should, but when you put 10,000 of them together, they can behave in all kinds of weird ways. So the question is, how do you test that? And so what we do is we started out by creating simulations. So these are fairly, I would say, naive simulations where we're simulating the network as it scales up past like 10,000, 100,000 peers. But that's really just kind of verifying that the topology self-organizes in the way that it should. Then the second step is a more realistic simulation where we're simulating the actual peer code is being used, but instead of using the TCP/IP stack, we use a simulated network stack, and that allows us to experiment with tens, hundreds of thousands of peers and validate the behavior there. And then the third, I don't know if I'd call it a simulation exactly, but literally what we're doing right now is we just fire up a bunch of peers on a single machine, and we use I forget the name of it, but we use a kernel plugin that allows you to simulate latency and packet loss. And we just simulate a bunch of peers on a single machine, talking to each other as if they're kind of remote on the internet. And then the next step is to release it and put it out there. And that is what I think we're very, very close to doing at the moment. I hoped we would have done it by this talk, but we're not quite there yet.
Awesome. Thank you.
All right, howdy. So I'm curious about, so these contracts have state transitions, so these contracts might be propagated throughout the world, as nodes cache them. I'm really curious, like, if there is, or what the mechanism is that causes the deltas that are created to have some like eventual consistency. Because it sounds to me like starts getting cached, and then I don't understand what pushes state transitions back towards the rest of the network. Or if there's any like guarantee of this happening, or like maybe people just make a bunch of requests and eventually it goes back and forth and back and forth, or
yeah. So this, I didn't get into this in this talk, and I'll try to summarize it. I think we've talked about this a little bit in the past, but so when you modify the state of a contract, you create, well, essentially you modify your local version of the state. So I guess a practical example. So you've got a contract out on the network. You're authorized to modify the state of that contract. So what you'll do is you'll make the modification to the data on your local peer. Your local peer will then be connected to your peer will be subscribed to that contract. So it's got a copy of the state in its own peer, and it's got upstream peers through which it's subscribed to the contract for updates. When you modify your local state, a separate mechanism will notice, it's like, oh, wait a minute, we have different versions of the state for this contract. One of us is probably out of date. And there's a protocol which will allow you and the upstream peer to efficiently synchronize your state so that it will propagate to the upstream peer. And the way this is commuter monoid. So the idea is that the update to the state will kind of propagate through the network like a virus, and it is inherent in how the contract is written to say, well, if I've got the contract provides something like a merge operation. Has to implement a merge operation, which means that you can take two states that are different and it will merge them in order to create a state that incorporates whatever the most recent state is, however the contract author wants to define it. So if the state was something like, let's say it was just a set of values, and if you have two sets of values that are different, the way that you merge them might just literally be that you combine the two sets, and obviously any duplicate elements would not be duplicated. But you can set the contract up in any way, like just a very wide variety of ways to define how state is updated. And then and then the state propagation is really kind of viral. So it's almost difficult. If you've got a peer that's subscribed to a particular state, it's almost difficult to, it would be difficult to prevent your peer from updating. And then there's a separate mechanism where if a peer notices that your version of some state is out of date and another peer has an updated version of the state and there's been a long delay there, then there's a reputation mechanism where a peer might decide that maybe your peer is up to some kind of mischief because it's not propagating the state updates as quickly as it should.
So the actual propagation part is the part I was mainly curious. So it sounds like when you do a write, you're pushing this out to a few different points of the network in practice, and then all those cache nodes, then like through their chain of whatever the subscription mechanism is, then they actually, that's how the delta gets to them, is they have this mechanism.
Yeah, it propagates through the subscription tree.
Okay, that makes sense.
Initially up and then kind of down and fans out to everyone.
Cool, thank you.
Sorry, I might have missed this, but how is location chosen?
The location of a contract is based on the hash of the contract WebAssembly. Okay. So the contract WebAssembly determines the location of the contract. In the case of a peer, the location is derived from a hash of the peer's public class C IP address. So the first 3 bytes of a IPv4 address.
Okay. All right, thank you.
Hi. I'm slightly worried about when things get evicted from the servers. How do you control that? Oh, this data, I care about it, I don't want to be evicted. But on the other hand, maybe the whole point of the system is that I don't want to have every single piece of data I care about because I have other friends. Oh, this piece of data, lots of people care about it. But if I see the number of people caring about it dropping, maybe now I want to have a copy of it. So how do you deal with this kind of thing?
Yeah, great question. So Freenet is really much more of a communication medium than a storage medium. And Freenet collectively works like a least recently used cache. So data is essentially cached in proportion to its popularity. If some data nobody is interested in it, then it can definitely fall out of the network. And that's necessary because otherwise the network would fill up potentially with useless data. There is one exception, which is if you are, let's say if you want to make sure that a particular piece of data stays in the network, your peer can subscribe to it. And this is like, we call it pinning. But essentially if your peer is subscribed to it, then it's not going to fall out of the network. But your peer actually has to do the work of subscribing to it. So you can keep data in the network if you want to, but you just got to do a bit of work. But generally speaking, Freenet's not about, this is like maybe a distinction between Freenet and something like IPFS. IPFS is kind of a decentralized Dropbox. Freenet is not about long-term storage of data. It's much more of a communication medium. Okay, well, thank you very much.